three examples. All right, so here's the first one. And this one is with regards to volume flow, okay, which is kind of, as you can see there, it's a division between the incoming, okay, and then the outcoming, which is kind of pipes that you have. So medication is being infused into a system, okay, so if the volume flow coming in and volume flow coming out are equal to each other, okay, so here is the volume, okay, which is coming in, okay, so it's coming in into three separate, okay, yet equal, okay, kind of pipes, and then the medication's coming out, okay, so it kind of fuses in. Now find the velocity coming in into each entry point in the figure, okay, so assume that the radius of the input is only 2 millimeters for all the entry points, so 1, 2, and 3. The radius of the output is 3.5 millimeters, all right, so it's not that much bigger, okay, but that's what we would have. Okay, so we have, okay, so the radius over here, okay, which is 3.5 millimeters. Okay, the radius in all of these right here is equal to, so maybe I'll put in, okay, I'll put out for that. This one is 2 millimeters. Okay, so this is what we have. Now, the volume, which is the volume flow rate, okay, which is coming out, is 30 milliliters per minute. So it's very slow, all right, and very tiny, okay, so that we have. So that's the volume flow rate, okay, so that's right there. Now, if this is true, then what you're coming in and what you're coming out are equivalent. And we have three, right? We have 1, 2, okay, and 3. So these three have to be equivalent to whatever's coming out. So now, how would we capture that? Well, so we would have 3 of these, okay, and the volume flow rate is always simply the area, okay, and this is for the individual one, okay, so which is the area coming in, multiplied by the actual speed, okay, which is coming in, okay, individually. Now we're assuming that they're all the same, okay, and there's 3 of them, right? So if you add all 3 together, okay, they should be equal to the total volume, which is, okay, the total volume flow rate, which is coming out, all right? So this is on the outside. So that's what we will have, and now we can try to substitute and then find out all the given pieces. So we have 3, okay, so the area, which is kind of cylindrical, so which is pi, this is going to be r squared, multiplied by VI is equal to whatever the volume flow rate output is. Now, all of these are kind of messed up, right? Because of the fact that they're not really in metric standard units. So if we try to change all of them to metric standard units, then we can deal with this. Now, they're asking us for the velocity. They don't tell us exactly what units they want, so we'll try to keep it in metric standards. And if we do that, it might be not a very convenient way, but we'll do it anyways. So first of all, okay, let's try to write these out. So this is 30 milliliters per minute, all right? So now, what is exactly 30 milliliters, okay, for every single minute in terms of the metric standard, okay? So this is the first component that I'll try to concentrate on in here. So we got to change this, okay, to meters cubed. And we have to change this to seconds, okay, in order to make this work. So now, first of all, okay, if you want to change this back to liters from milliliters, so this is going to be just 0.03 liters, okay, per minute, right? That changes it to liters. Now, from liters to meters cubed, we have to still divide by 1,000 because there's 1,000 liters in every meter cubed. All right, so what that means, okay, is that if you're going to be doing this, so if you take this and you still divide it by 1,000, okay, then this is all of a sudden going to become, so I'm going to just rewrite this. So this is going to be 3, okay, 0.0, I'll just write it like this, times 10. Now to the negative, okay, this is going to be -5 if you want it liters per minute. All right. So, how does that come about? Because if you take 0.03 and you divide it by 1,000, that's going to be another 3 decimal places, which is going to shift to the left. So this is going to be now 3 times 10 to the negative 5, because it already has 2 decimal places. So divided by another 3, okay, that's negative 5. Now, we want to get rid of the minutes, all right? So with regards to that, so that means for every minute, there are 60 seconds, okay? So this now becomes 3.0 times 10 to the negative 5. Now, all of a sudden, okay, so we can now get rid of the liter, because now it's meters cubed. Okay, then this is going to be now meter cubed divided by, well, a minute is 60 seconds. So now, okay, so you can certainly take the numerator divided by the denominator. I'm going to leave it here for just a moment. On the left-hand side, so this is going to be a little bit easier for us to work with. Our radius is in millimeters, right? So this is in millimeters in here, and we want to change it back to meters. So, you know, within here, so there's going to be 0 point, okay? And now we're going to have to try to jump in 3 decimal spots. All right, so this is going to be now in meters. So that's my radius, right? So that's from meters. If you go back from millimeter, so that's metric prefix, change it back, milli, okay? So it's going to shift over to the left 3 spots, all right? So now that's going to be pi times 0.002 squared, and so that takes care of the area times our VI. So if you want VI on its own, so there's going to be VI is equal to, so now I can rewrite this since everything now is in metric standard units. So that's going to be this divided by that 60 seconds, divided by the 3 from here, and then divided by the pi, and divided by the 0.002 squared. All right, so this is what I have right there, okay, equals. Okay, so now with all of that, it's probably the units that are going to be the hardest to deal with, so I'm going to put this in brackets. So 3 times, this is 10 to the exponent of negative 5, that's my numerator. So that entire thing is going to get divided by, and I have to put all of that inside there, so 60 times 3 times pi, and then times, okay, the radius, which is 0.002 squared. Okay, now let's divide that in, and it's going to be tiny. So 0.013269, etc. But now it is in meters per second. All right, so if you wanted to do that, you want it in centimeters, so 1.3 centimeter every second. So that's what it would be. In terms of the, so now I have 2, I guess 2, there's only 1 sig fig, okay, which is your lowest one. You know, so if you want it rounded to 1 significant figure, it would have been 0.01 meters per second. So that's the work in order to complete this example. The hardest component is your units, right? That you have to kind of change everything back. But it's a nice refresher on thinking about units, okay, and knowing and understanding how important they become. That's it for this one. Here's the next example. So a medical test is trying to approximate the number of capillaries in a patient. On average, okay, so this patient's heart pumps 28 liters per minute. The patient's aorta has an approximate diameter of 1.02 centimeters. The measurement of the speed of the blood in the capillaries is approximately 1.2 millimeters per second, okay, and we'll assume the radius is about 11 micrometers. Now, of course, this changes in humans, but in general, you'd be shocked, okay, so how many capillaries we actually have, okay, because the answer is going to be actually in the billions. So we want to be able to approximate how many capillaries would this patient have, okay, based on this data, all right? So let's think back, okay? So in terms of volume flow, so what we have is, we have our aorta, all right? So our aorta has a certain flow rate, okay? So this is coming in from the aorta. And if the amount, okay, of blood that is passing through, okay, is going to be keeping this actual volume flow rate constant, okay, so throughout, now, of course, the aorta starts to split up, right? And you have more and more and more until you get into capillaries where they're, you know, very fine and tiny. So what's going to happen is, yes, you know, we do have a certain amount of volume flow rate in the capillaries, But we have a lot of these capillaries. Okay, so now how many of these capillaries will we have? This is what we're asking. I'm going to designate it as n, where n stands for the number of capillaries. All right, so they actually tell us in here that we have 28 liters per minute that the aorta is pumping at. Now I'm going to start changing all of these to metric standard units so that I can just kind of follow through, okay, on this, okay, so that it's all easier to be able to calculate. Not that it will be easier, because I can see that there's a lot of different units in here. So first of all, let's change this. Now, there's 1,000 liters in a meter cubed. So that means this is going to be 0.028 meters cubed. And a minute is obviously 60 seconds, okay? So that's not very difficult. So, okay, let's make my life a little bit easier. So I'm going to put this in, divided by 60. And, all right, well, okay, so it's not easier at all. So 4.6, okay, all these sixes times 10, and that's what? 1, 2, 3, negative 4. Okay, now that's in metric standard units, so meters cubed per second. That's my left-hand side. All right, so that's that. Now on the right-hand side, so now I want to figure out this. They do give me what the actual speed is in the capillaries. Okay, that's right here. That's in millimeters per second. And then they give me what the radius, okay, of that is. So we'll assume that it has an area, okay, of a circle. All right, so what that means is this is going to be area of one capillary times whatever speed is moving in that capillary. Now the area is pi r squared, and then this is, okay, the C just stands for capillary. This is the speed itself. All right. So now let's, try to put this in. The problem is, notice that we have 11 micrometers. Well, 11 micrometers, that micro is 10 to the negative 6. So it means it's 6 decimal places we would have to move. So this is going to be, and you can double check for yourself, this is going to be equal to this in meters. Or you can just write it as 1.1, okay, times 10 to the negative 5, okay, meters right there, okay, and that should make sense to you as you move the actual decimal place over. All right, so that's my radius, okay, so that's going to be my radius over here that I'll substitute momentarily. My speed is 1.2 millimeters per second, 1.2 millimeters per second. This one's a little bit easier. So again, you can check this, and this is going to be times 10 to the negative 3 meters per second if you move the decimal places 3 over. Okay, so now I have all of that. Now I have to substitute this this whole thing in here. So if I take all of this, now this is going to be a tiny number because these scientific notations, okay, that I'm dealing with are going to be rather small. All right. Okay, so how am I going to do this? I want to be able to solve, okay, for n, which is right here. So that n, let me just change this back. That n is going to be equal to the volume flow rate, okay, in the artery, which is over here. That's on the left-hand side. And then I'm going to have to divide this whole thing by the volume flow rate, okay, in the capillaries, okay, to get the number of capillaries. And that is all of this junk. All right. So I'm going to have to substitute all of this in here into the calculator to actually obtain my answer. All right. So let's do that, together. So I have, okay. So I already have this on the calculator. So this is my left-hand side. That's this right here. Okay. Now I'm going to have to divide this by, okay. So this whole thing divided by, I'm going to put it all in brackets. So notice I'm dividing by pi, okay, this is pi. The radius, so it's going to be times the radius, okay, on its own. Now that radius, so I'm going to put it in brackets there, which is going to be 1.1 times 10 to the exponent of negative 5. That's my radius. I want to square this, all right, so that's squared. Okay, so I'm right there. So this is what I'm doing. I put in pi. I put in this, Now I have to multiply by the speed. Okay, so that's 1.2. Okay, this one's going to be easier to put in as a decimal actually. Okay, so that's 1.2 times 10 to the negative 3. Okay, so there you have it. So I've just substituted all of it in. Okay, and I'm going to hit equals. Okay, and as no surprise, as I said, so n, okay, this is in the billion range, right? So 1, I'm going to just keep it to 2 sig figs here, times, 10 to the negative 9. This is the total number of capillaries. And of course, this ranges, to be honest with you, is probably higher than that, okay, within here. And you can certainly take a look. I've run into this question. I've actually put in here, okay, right there. So I put a little footnote, although you can't see it. OpenStax is a really nice textbook, which is the physics, okay, college physics that you have, second edition. And I think in chapter 12, okay, when they talk about the volume flow rate, I ran into this at some point. So they do actually also do an example like this. So if you want to check it out, okay, you can do so. I'll put a reference in the description, okay, to that. All right, so that is it for this example, okay, very exhausting, especially changing it back to metric standard units. Here's the last example for this video. So it says a research team is doing testing on blood flow, speeds, and pressure. So in a horizontal tube, the blood has an initial pressure of 120 millimeters of mercury. And they give us what the conversion is at a speed of 35 centimeters per second. Okay, so that's how fast it's moving. Eventually, the tube narrows and flows at a speed of 65 centimeters per second. So it's almost twice as fast. Assuming the flow is at the same horizontal plane and the density of blood is 1.03 grams per centimeters cubed, find the pressure, all right, in the narrowing tube. So what this would look like is something like this. Okay, so you would have, so here's your tube, okay, and I guess, they're saying that this thing narrows down. All right, so I'm going to duplicate this back in. Okay, so this is what you would have in there. Okay, and it would just kind of narrow down, kind of like this, right? So this is what we would have. So this blood is flowing in. Okay, this has a certain pressure. So let's call this P1. It's 120 millimeters of mercury. Okay, then as it narrows, it will have a certain different pressure, P2. Now we want to be able to find what this is. Now they tell us all kinds of information in here. So we know the density. Okay, so now notice the density. I'll change it actually to metric standard. So this is going to be times 10 to the 3, okay, meters cubed per, meters cubed. This is kilograms per meters cubed. So kilograms per meter cubed. And that is when you're going from grams per centimeters cubed back into metric standard of kilograms per meter cubed, you multiply by 1,000. So that's why the 10 to the 3, right? So you can convince yourself if you want to do the unit conversion. So that's from right there. So I have the density. Now I have all of the speeds. Okay, so notice that the speed initially is, I guess, 0.35 meters per second over here. And the speed over there is 0.65 meters per second, right? Because centimeters to meters is easy conversion. So I have all of that. So I'm going to have to use Bernoulli's principle in order to solve this. Now, what does Bernoulli's principle tell us? It tells us that the pressure, okay, plus 1/2 the density of the speed squared is equal to, okay, so this is on this side, is going to be equivalent to what we have on the other side, which is pressure 2 plus 1/2 the density of V2 squared. Now, these particular pressures, so since I have everything in metric standard units, so I can certainly change that. So that 120, so this pressure right here, so that 120 millimeters of mercury, right, I can obtain. So 1 millimeter of mercury, they give us what that conversion is, which is 133.322 pascals. All right, so I'll have that. So let's see what that would give me. 120 times 133.322. So it's quite a lot, but so be it. 5998. I'm not going to round anything in here, so that's this one. And so now the next component, so if I want to find out what this is, so plus, okay, so I have all of these, so I'm going to actually put this in here. So 1/2, which is 0.5, times the density, and that density was 1.03 times 10 to the 3. Okay, so 1030. So that's the density, multiplied by the speed, 0.35. All right, except that has to be squared. So that's going to be that right there. So that's actually super tiny. Okay, so this is what we have. Okay, so within here, so this is meters, okay, and it's squared. Okay, so right there, so it's very, very tiny. Okay, so that additional term, so that will be 63.0875, so it's not going to have that big of a difference. And then on the right-hand side, so P2, okay, so plus, and we have that other term, so which is 0.5 times the density, 1030, right there, and multiplied by its speed, okay, which is 0.65, okay, squared. Okay, so that's also tiny. So it's 217.5875. So now I can solve for P2, right? We can bring this whole thing over on the other side and then solve for what that P2 is. Okay, so let me do that in quick fashion on the calculator. So I'll take those two numbers and subtract this one, and we'll see what we get. So there you have it. All right, so that's what we would have. And now if you want to change it back, so if you want to take this answer back into millimeters of mercury, you know, you can do the conversion, okay, and you'll find out. So this is 118.8, all right, okay, which is millimeters of mercury. So it's not a very big drop, but that's because this just went from 0.35 to 0.65, okay, which is not a very big change in terms of the speeds, okay, that this thing is moving at. Okay, so that's what you would have it. If you want to round this off, okay, this looks like it's, you know, two significant figures, okay, then this would have been actually rounded back off to 120 again. Okay, so it looks like the pressure hasn't really changed at all. All right, okay, so there you have it. Okay, that completes this set of questions for this video. Thanks for watching. Bye, everybody.